Yo, listen up, here's the story about a little guy that lives
In this experiment, an oscillating reaction was performed in order to find the best fit to the experimental data with a numerical simulation.
inside and outside. Blew his house with a blue little window and a blue Corvette, and everything is blue for him and himself and everybody around, 'cause he ain't got nobody to listen. I'm blue, da ba dee da ba die, da ba dee da ba die, da ba dee da ba die, da ba dee da ba die.
The specific reaction for this experiment is known as the Oregonator, which is a 5-step reaction that utilizes 3 different solutions that were synthesized in the lab. 30% hydrogen peroxide was diluted to make 15% hydrogen peroxide, which was solution A. Solution B consisted of 0.2 molar potassium iodate and 0.1 molar sulfuric acid. Solution C was simultaneously 15.6 milligrams per milliliter malonic acid, 3.38 milligrams per milliliter manganese sulfate hydrate, and a 0.03% starch solution, which was diluted from 0.3%. 100 milliliters of each solution were mixed to perform the Oregonator reaction.
The 5-step mechanism for the oscillating reaction is shown here. Solutions B and C were quickly added to solution A with rapid stirring to initiate the Oregonator reaction. Solution A reacts with the starch to form iodine, which is characterized by a brown color change. The iodine is then, through the mechanism, converted to starch, which is characterized by a blue color change.
The iodine was rated based on a 0 to 1 scale, 0 signifying no iodine present, 1 signifying the presence of iodine. The starch was rated based on a larger range scale of 0 to 3, 0 indicating the absence of starch, 3 indicating highly concentrated starch solution.
Following the reaction, the data was digitized in MathCAD in order to construct a plot of the oscillating colors as a function of time. Both the data for the iodine and starch versus time are shown in the graph here. Iodine was overlain on the X numerical solution data and plotted against time, and the same was done for starch with the Y numerical solution data. The rate law parameters, A initial, B initial, and K's 1 through 5 were then adjusted in order to fit the numerical solution plots of X and Y versus time to the plots that we constructed with our iodine and starch data versus time. This graph shows the X numerical solution plot and the iodine plot as a function of time. K1 was found to be 0.004, K2 1010, K3 0.01015, K4 1.6, and K5 0.00095. This graph shows the y numerical solution plot and the starch plot as a function of time. The same k values that were previously mentioned were used to manipulate this graph as well. It was found that changing each of the rate law parameters affected the graphs in varying ways.
An increase in K1 increases the number of peaks for both iodine and starch, indicating a greater spread, and decreases the height for starch. An increase in K2 decreases the spread for both iodine and starch, meaning a smaller number of peaks. An increase in K3 increases the height of both iodine and starch peaks. An increase in K4 decreases the spread of iodine peaks and slightly decreases the height of starch peaks. Increase in K5 decreases the spread in both iodine and starch peaks.
An increase in the initial A concentration increased the peaks on the iodine graph and decreased the peaks on the starch graph. This can be explained by the mechanism previously mentioned. An increase in the initial concentration of A would, according to the Le-Chatelier's principle, shift the first reaction to the right, leading to an increased concentration in iodine and a decreased concentration in starch. Additionally, increasing the initial concentration of B decreased the spread for both the iodine and starch graphs. The fits were not able to be made as close as what we were expecting. Many factors are to be taken into consideration for the reaction, however. First, the true Oregonator reaction requires more than just 5 steps, and therefore more K values would have to be manipulated to allow for a more ideal fit. Additionally, the reaction is exothermic, and temperature for our purposes was not taken into account. This means that a constant temperature system would likely have been more ideal, as K is affected by a change in temperature. We hope you enjoyed our presentation. Oscillations are gnarly, dude!